off now. Yes, I'll take care of it, don't worry. Do you want it? That's okay, isn't it? Yeah. Alright, now, what we're going to have a look at today elasticity. Okay. Now, we did a little bit of this. Just turn this off. We did a little bit of this in semester 1. If you think back to Hooke's law, do you remember Hooke's law? What's Hooke's law? Just as a formula, yeah. K delta x, yeah. So we just need to think back to that. What we're going to talk about today is elastic materials. Okay, elastic materials. Like a spring, rubber band, stuff like this. So firstly, some definitions. So first definition is of the word deformation. Does anyone know this word? No? Not quite. Close.
Losing form.
Yeah, not quite actually. Well, yeah, close enough. They're much simpler. Yeah, what's it? Change in shape. No, that's a particular deformation. But deformation by itself just means change in shape. Okay, so deformation, change in, and I will say, they could ask you this in the exam, what does it mean? So it's a change in shape or size of an object due to a force, or, I wonder if anyone wants to give me the second reason that could change a shape. Force will change a shape, of course. Anything else that might cause a change in shape? Heat, yeah. Due to a force or change in temperature. Okay, so make sure you have that written down, because the exam could say, for 1 mark, what does deformation mean? So it's a change in shape or size due to a force or temperature change. You got that? Can I scroll down? Okay, so if we go now back to the force, there are 2 types of forces here that can cause a deformation. The first one is a tensile force, and then the second one then is a compressive force. So this sounds like very fancy words, but does anybody know what a tensile force is?
Extension?
Yeah, keep it simpler, but you're right. What's a simpler word for extended?
Stretch.
Simpler?
Push.
Pull, yeah. So tensile force, that just means a pulling force. So, compressive force? Push, yeah. I'm just giving you the simple word. Just so in the exam, if the question says there is a tensile force, you might think, what does tensile mean? It just means pull. Or if there was a compressive force, it means push. Okay. That could be important for like a spring. Are you pulling the spring or pushing the spring? Okay. Right, next. Oh yeah, and there's one more which isn't on the exam, but I'll do it since I'm doing all 3 of them together. Torsion. Anyone want to have a guess on that?
Push and pull.
Well, kind of. No, not push and pull.
Squeeze.
Squeeze, no. Anything else? No. Think of words like push, pull, squeeze, not this. What else can you do to something? Stretch, no.
Release.
Release, no.
Friction.
Friction, no, way off. Twist. Twisted.
It's almost.
And it's almost push and pulling, yes. Okay. So these are all fancy words, but they simply mean pull, push, twist. That's all. Okay. Now, there are two types of deformations. Can I scroll down? Yeah. So the first type we'll look at is elastic deformation. Elastic deformation. Anyone want to have a guess at what that means? So we know what deformation means, and we know what elastic means. So what do we think?
When the material is elastic.
Oh, no, too complicated.
Elastic, yeah.
Go Daniel, what do you think?
Elastic.
No, too complicated. We're not there yet.
Changing elasticity.
No, it's difficult to start.
Changing the form.
Yes, so it's a change in form, but in what way? It's special. Oh, you have it the wrong way around, Mohammed. It does go back to its original shape. So this type of deformation is, and the key word here, reversible. Okay. So in other words, if you remove the force, it returns back to its original shape, like an elastic rubber band. No force, the shape goes back. Okay. So no force, that means returns to. Sorry. No force means back to starting shape, whatever it was. Original shape, whatever. No longer deformed. Okay, so does anyone know what the opposite of this is? Normally, yes, inelastic. Inelastic is fine, but there's a special word here. Plastic. Yeah, plastic deformation. This type of deformation is not reversible. It's irreversible. Is not reversible. So we have elastic deformation and plastic deformation. Can I get some examples of elastic deformation? Spring? What else? Rubber band? Yes, your clothes, anything you're wearing, it stretches and then when you take it off it goes back to its shape. What about plastic deformation? Yeah, my cup of coffee would be a better example. Huh? Glass, yeah. Yeah, what else? Wood. You know, if you manage to twist, like if you think about a barrel, okay, barrel. You twist the wood into a barrel shape. The wood doesn't go back to its flat original shape. Huh? Plasticine, yeah. Play-Doh, yeah. Anything else? Yeah. So, you also realize though that some things which we think, like take clothes for example, like here, my scarf. We think of this as being elastic because if I stretch it, it'll pull back. But some things, or no, all things that are elastic, you can only stretch them to a certain point, and then when you let go, they don't return back to its shape. Okay. So this is, I think, what people were saying earlier about elastic limits. You know, things that are elastic are only elastic up until a certain limit, and then after that they no longer are stretchy. Okay, they become plastic then. Okay, so we just need a couple of more words before we start here. Yes, I'll give you a graph here. So, a graph here. So this is extension, and then this is force. So we know from Hooke's law, what's the formula for Hooke's law? F equals K delta X. So the graph should look like this. And what's the slope of this graph? What's the slope? It's K, isn't it? Because of this formula. Yeah? For this part, it is elastic. But like I said, if you increase it too much, then it loses its springiness. Think actually about a spring. Do you look? If you have a spring and you stretch it too much, then it turns into a wire. You know, if you stretch it really far, then it's a straight wire. Then if you let go, does it snap back? No. So there's a limit. So it'll be like this up until a certain point, and then this point here is called the elastic limit, funny enough. Elastic limit. And then after that, gets all weird then. It's no longer a straight line. So it's elastic up to here, and then it's plastic up to here. I don't know, because it doesn't necessarily break into two pieces. So I don't think you could call it breaking point unless you know it broke, you know. Elastic limit is a bit more general. It is a type of breaking point though. How's my battery doing? Yeah, I'm okay. Alright. In the exam, this is common enough question in the exam. I mean, like maybe once every 4 exams, they'll ask you to draw a graph that explains elastic limit. So this is exactly what they want. If you draw this, you get the full marks, okay? So this is a graph that explains elastic limit. I think actually if I look at the exam question, the question would say, sketch force against extension, label elastic limit, label plastic deformation. So that's what you need there. Okay. Now we can have a look at some formulas. Can I scroll down? Yep. Okay, so formulas now. Stress and strain. And just before I give you the definitions, you need to picture this in your mind. If you have like something like a rope, for example, so I don't know, this is my rope here. And here there is a force pulling it. And here is the area. And when you pull it, the rope moves a little bit, delta X. So this is what my letters mean, okay? So you might want to just do a quick drawing of that. I'm using a rope as an example. Doesn't need to be a rope, it can be anything. Got that?
Yes.
Yeah. Okay, so the definition Well, I wonder if anyone knows these words, stress and strain. Does anyone know stress?
Yeah, force.
Yeah, it's force divided by area. And does anyone know strain? Yeah, it's the extension over the original length, which I should have actually drawn in here. This, and then it's originally x long. Okay.
Could you repeat it, please?
Well, there it is there. Strain is the extension divided by the original or the natural length. And what's the units here? Yeah, which is the Pascal, isn't it? And then the units here? No units. No units. The diagram? Yep. Well, while I'll plug this in while you're doing that. Yeah, okay. Okay, can I go on? Alright, so we have this, and then finally we have some, well, if people know stress and strain, they probably know what I'm going to do next. Young's modulus, yes?
What do strain pricing imply?
Yeah. Strain is a bit like a percentage. It tells you how much it's been deformed, how much of a change in its shape has taken place. So, for example, if I have 1 meter of rope and it extends by 1 centimeter, then the strain is 0.01 or 1%. So in other words, strain just, it tells you how deformed it's become. Stress is a pressure, basically, force per area. So this is easier to picture. Strain is a measure of deformation. Yeah, okay. So good job, you're all set. The next thing we're going to look at is Young's modulus. What letter did you use in high school? Yeah, I've seen some books use E, okay, I'll stick to using Y. It's a capital Y. Yeah. Young's modulus, what do you recall what it is? Stress over strain. Yeah. So this is 3 important formulas for now.
Is there any other formula?
No, well, except for, of course, your basic formulas for calculating areas. So for this rope one, what formula would I use for area? Pi r squared, because it's a circle, yeah. Yeah. We could try and get some meaning here if you want, but I mean, if you look here, if you think about this, if you were deforming an object, which of the 2 things are you more likely to change, the stress or the strain? If you were doing an experiment to calculate Young's modulus, for example, what thing might you change in the experiment? Not like with the rope. You can't really change this, can you? Because that's what happens when you apply a force. Can you change this? No, not really. Can you change this? No, but can you change this? Yeah, so we think of stress is what we can change. So if you want, you can rewrite this as strain equals 1 over y times stress. Because you can imagine, if you had a rope, you could put different weights on it. Different weights would represent different forces, and different forces would mean different stress. So what type of graph should I get here? If I put stress here, whoops, stress here. Yeah, so what type of graph? I should get a straight line, shouldn't I? And the slope of this line would be 1 over Young's modulus. So different materials would have different slopes, depending on how elastic or plastic they are. Let's try and imagine a rubber band, okay? So if I go back up here, if I had a rubber band, what do you think happens to the strain if I increase the stress? If I increase the stress a little bit, what happens to the strain? Does it increase a lot or not? It'll increase a lot, because if you have a rubber band and you put more weights on it, it will stretch more. So what does that mean for the slope? Here, it will be bigger. Yeah? So what does that mean for Young's modulus? It'll be smaller because it's 1 over. Yeah? So in other words, it's more elastic with a smaller Young's modulus. Okay? So, well, okay, if we picture, yeah, so if you look here, if I have something like my scarf, okay, look up everybody, if I put 1 weight on it, it moves a bit. If I put more weight on it, does it move much more? Not much more, okay? So as I increase the stress, the strain increases a little bit. Now, if I had a rubber band, does anyone have a rubber band? Give me your necklace. Thank you. If I put the same weights on it, it increases a lot more, doesn't it? Yeah. Don't worry, I won't break it. It looks expensive. So if I increase the stress, I get more extension, which means more strain, bigger shape. So that means the slope is bigger. So for his item of jewellery, the slope is bigger, so Young's modulus is smaller, okay? So small Young's modulus means it's not very elastic. Sorry, did I say that backwards?
No, more elastic.
Yeah, small Young's modulus means it's more elastic. And a big Young's modulus means it's less elastic. Hang on, we have to make sure we're getting this right. His item here has a big slope, it's elastic, small Young's modulus. Yeah.
So more elastic, smaller.
More elastic, smaller Young's modulus. It's opposite like that, yeah. Okay, so let's have a look at using these formulas now. Oh, and of course, don't forget, again, this will be true up until a point where maybe it breaks or something. Okay. Right, let's have a look at some examples. Okay. Oh, sorry, before I go on, what's the unit for Young's modulus? Pascals as well, Newton per meters, yeah. Okay, so let's take our first example here. I have 1 meter of brass wire with radius of 1 millimeter, and the Young's modulus for brass is, let me see, 0.76 micro. Oh no, sorry, that's not it. Not micro, of course. It's usually very big. 1.01 multiplied 10 to the 11 pascals. So my question would be, if I hang, I don't know, something kind of small, 100 grams from the end of the wire, then what is the extension? So I have my brass wire, I put a weight at the end of it, and it will extend a little bit. So I'll give you a minute to try it first for yourself, using the formulas I've given you, and then I'll show you how to do it. But I'm sure some people will be able to do it. I want to know what is the extension. Now wait, before you start, are you expecting a big or a small number for this extension?
Big.
Now think what it is, it's brass wire.
Small.
Small, like a millimeter maybe. So, see if you can do it, and I'll do it now in a moment, once you have a chance to try it. Okay, I'm going to do it now. Keep working if you know what you're doing. So, let's see. If I draw what I have 1 meter here, and then I hang my weight on it, and it will extend by delta x. The force pulling it down is equal to the weight, which equals mg. And what did I say the weight was? 100 grams, yeah. So, it'd be equal to 0.1 times 9.81, so that is 0.981 newtons. Now the area of my wire, the area is pi r squared, which equals pi 10 to the minus 3 squared, so that's pi times 10 to the minus 6, because it's a millimeter in radius. So I have Young's modulus equals stress over strain. So that means strain, it's not the one I want, strain, because that's the one with the delta x in it, is stress divided by Young's modulus. Strain, delta x over x equals 1 over Young's modulus, force over area. So I get the formula here, delta x equals x over Young's modulus, force over area. So that's 1 over, what is it now, 1.01 times 10 to the 11? Yeah. Times 0.981 over pi 10 to the minus 6. So here I would get roughly, now I'll just do it roughly, but you have a calculator. So very, very roughly, this almost cancels with that, and the pi would be about a 0.33, and then that would be about 10 to the 5, so roughly 0.33 times 10 to the minus 5. Now if I divide it by 10 to the minus 3, that would be millimeters, so that's 10 to the minus 2. It's going to be, actually, if I do 10 to the, I'd make it 10 to the 6, 10 to the 6, no, 10 there. 3.3 micrometers roughly is what I got. 3.092 micrometers. Yeah, so my rough estimate's not so bad. So roughly 3 micrometers is how much it moves. It's not much. You won't even be able to see that. But you can still know that it has extended by this amount. But of course you can't see this. It's way too small. Okay. And let's see, what else? Do I have another example to do? Oh yeah, I suppose I haven't really given you the definition of Young's modulus in words. I've given it to you as a formula. So, what would you say Young's modulus is in words if you were to give the definition?
The ratio.
Very good, yes. So because it's a fraction, is the ratio of stress to strain in a material. And now you have to say what each of those are. So what's stress? Stress is force per unit. Force per unit. And here's a very important word here. Cross-sectional area. Yeah.
How do you get 10 to the minus 6?
That was 10 to the minus 3 squared for the, I did a pi r squared formula to get the area of the cross-sectional area. Stress is the force per unit cross-sectional area, and strain is the ratio of extension to natural length. I wrote probably, well, no, not probably more. That definitely would get you the full marks in the exam. Young's modulus is the ratio of stress to strain in the material, and stress is the force per unit cross-sectional area, and strain is the ratio of extension to natural length. In other words, I've put in the formulas I gave you earlier into words. Well, I won't go back up to it. Write this down, please. You have that written down? Yeah. So I'll do the same thing I've been doing with the other material sections. What you doing, Tash? I'll do the same thing I've been doing with the other material sections. I'll give you the questions, and then the next lesson I'll go through all the problems on the board. Okay? Which I think is, because we have more time in semester 2, I can do this. Okay? So there's 8 questions, like what I just did on the board, and it shouldn't take you too long to do, maybe about 15 minutes. So you'll have to finish them at home. Okay? Finish them at home. Now, hang on, the next class we have is tomorrow. Is it 1 or 2? Yeah, but I might not need the full double class. I might need like a class and a half on Excel. So I'll do the Excel first, and then I'll do the answers after Excel. So please bring your laptop. Okay? We only have 2 lessons left in materials, and then the materials section covered. And then we go on to fields. And then after fields is the atom. Then after the atom we'll do the exam. Yeah, that's in the section on the atom, yeah. Okay, you can try these now, please. So there's no answers because I'm going to do them in the next class. But they're not too difficult. No. Nice try, though, Joshua. Good to ask. You didn't ask, you'd never know. Here's one for Dana. Yeah, just work on these for a few minutes. Then you can go.